Good day everyone, welcome back to my channel, and in today's video we'll be discussing PDE, partial differential equation. Actually we are supposed to start with normal differentiation and integration, but we tend to just start this class with partial differential equation. However, we are still hoping to make other videos on differential equation and the type of differential equations, then integration. So introduction to partial differential equation. Now looking at this slide, we have some already what existing constant multiple rules. We already know what the normal differentiation. So we assume we already know the uh, the normal differentiation, the rules of what the normal, if you're talking about the sum rule, the product rule, the chain rule, power rule, and what other rule. You can pause this video to at least go through those basic formulas that we applied in partial in ordinary differential equation. These are what the basic what differential rules. Why this? Yeah, these are some of the rules. Also, you can pause the video to check them. I think the last one here is what the inverse word cotangent. You can pause them to go through. Now, what is PDE? What is potential? What is partial differential equation? Partial differential equation is an equation involving one or more partial derivative of an unknown function of two or more independent variables. So what we are talking about in partial differential equation, it means whatever you are differentiating, you have more than one independent variable. Like looking at this now, looking at this, we have with respect to x and with respect to y. Since it's more than one, then it means it's what partial differential. So the second derivative of u with respect to time variable t, this it means here you are differentiating, although here you are differentiating with t, but in two different scenarios. And here also, now it means for partial differential equation, we can decide to use this dot notation, or we can decide to use this approach, or we use this symbol here. Now normally this is what the actual symbol of what partial differential equation. However, when I have what u of x, what it means is what the partial differential of u with respect to x. Then if I have what u of xy, it means I have what second order here. I differentiated partial with respect to x and then with respect to y, so which is the same thing as this, right? And it's the same thing with this. So this one, it means I've differentiated partially in two order, in second order, with respect to t twice, then with this with respect to y. This one is mainly denoted with with space variable. So function of several variables. So a function of two variables, we have z. Z is a function that depends on x and y. So it means if I want to look for partial differential of z, I can look for it in terms of x and then in terms of y. So we have so from here, z is what the dependent variable, while the x and my y are what is independent variables. It means my z depends on these two factors, x and y, while my x and y did not depend on z. That's what it's saying. So we have one example here. We have f is a function of s comma y equals s square y plus 3xy square. So here z depends on both x and y. Don't forget, here is this complete function here is z, not just f is z, right? So it depends on x and y. Now also, in general form of partial differential equation, PDE is given by this expression. This is the general form of a partial differential equation. partial derivative measures rate of change of a function with respect to one variable, keeping the others constant. So what it means is that when you are looking for a partial differential equation for a partial derivative, then if for instance if you are differentiating with respect to x, then it means you differentiate with respect to x and keep y constant. So a good example is we have f of x comma y equals x square y plus 3x y square. Okay, now look, this is a good example. You have you differentiate z with respect to x comma, then you differentiate with respect to z with respect to to y. So now differentiating this, it means if this is the function f, then it means that we have the f dx. The f dx, it means I should differentiate this complete function with respect to x, right? So differentiating this, I will have 2x y. So with respect to x, then I'll differentiate this, then I will have 3y square. Then if I'm differentiating it with respect to y, then it means I should have this will remain constant, this will give me 1, so we have x square. Then I will differentiate this, it will give me 2y, right, which will multiply it to give me 6xy. So it means I have differentiated this partially with respect to x to give me this, since it's comma. Then I'll differentiate it partially with respect to x, with respect to y, to give me this. When I was differentiating this with respect to x, I kept y constant. But when I was differentiating with respect to y, I kept s constant. So numerical analysis provides a systematic framework to approximate the continuous solution of a PDE at discrete points in space and time. So a PDE is either linear or non-linear. A PDE is said to be linear if the dependent variable u and its partial derivatives appear only to the first power and are not multiplied together. So a general the general form of a second order linear PDE in two independent variable is this. As you can see, here you are differentiating u, right, with respect to x and y. So you will not see a function here that is multiplying u. Otherwise, if you see a function here, a derivative, and is also multiplying u, then it means it's not linear. But this one is a general formula for a linear PDE. So where the coefficient my a to g are constant, or functions of x and y, they are not functions of u. Once they are functions of u, then it means that equation will not be linear. So they are classified based on what the discriminant is. Now here are some examples of linear PDE of second order. Now we have this. It's called one-dimensional wave equation, right? Whenever you have an equation that satisfies this, then it means it has satisfied wave equation. Now if for instance we are given an equation with respect to t and x, maybe, and u, then it means you have to look for the second order derivative, partial derivative with respect to t. Then also look for a second order derivative with respect to x. Then you equate it to check if it can give you this. If it did not satisfy this equation, then it means it did not fulfill the wave equation. Then we have the second one, which is for one-dimensional heat equation. Now for heat equation, this is first order, unlike this is in second order, but this still remain the same. So for heat equation, and the third one, two-dimensional for Laplace equation. For Laplace equation, you have second order. Whenever you sum them, don't forget for x and for y, when you sum them, it will give you 0. But if you sum them and it did not give you 0 for x and y, it did not give you 0, it give you a function, then it's called a Poisson equation. Then we have another one two-dimensional what wave equation. So if you look for the second order derivative and it gives you something like this, so this one is for the u respect to x, respect to y, you sum them and it equates this and it gives you a constant, then it means for two-dimensional what wave equation. Don't forget we have mentioned a wave equation before, which is this, right? You see, for this wave equation, we call it what one-dimensional wave equation. It has only u with respect to t, then u with respect to s. There's no with respect to y. That's why it's called what one-dimensional. But the one that is what two-dimensional, it has with respect to x and with respect to what to y. Then we have three-dimensional what Laplace equation. We have with respect to x, y, and z. When you sum everything off, it will give what 0. That's what still Laplace. Don't forget, for Laplace in second order, when you sum them up, must give you 0. But if it did not give you 0, it gave you a function, then it's what a Poisson what equation. Now let's continue. So a PDE becomes non-linear when the unknown function u or its derivative are raised to the power greater than 1 inside non-linear function, like you have sine u comma e to the power of u multiplied together. Now let's give what a good example, like what this Burgers equation. As you can see, you have partial derivative of u with respect to t, plus then you are having u multiply partial derivative of u to x again. Just because of this function, then this equation is not linear. Then you talk about this viscous Burgers equation again. You have the partial derivative of u with respect to t plus u. Because of this u is multiplying what this derivative, then it means it's what is not what linear. As you can see also, inside the function you are having a u function again, so because of that is what is not what linear, and this one is what Fisher's what equation. So now find the partial derivative of the function z equals x cubed plus y cubed minus 2x squared y. So what you do, looking for the partial derivative, you have x, you have y. So you look for a partial derivative of y with respect to x, then you look for what with respect to what to y. So the first one, let's look for with respect to what to x. So we have partial derivative of z with respect to s. So differentiating this with respect to s, so this will give me 3x squared, this will give me 0, then here minus remain. So if I with respect to s, this one will give me 4xy. So I will have this, right? So I will have this. So removing my 0, I have this, which is 3x squared minus 4xy. So with respect to y, so I should come here and differentiate this with respect to y. This will give me 0, which is this. So this will give me 3y squared. So this minus is here. So this one will give me 1. So it means I will see about minus 2s squared, which is this. So after differentiating this with partial derivative of this with respect to x, it gave me this. With respect to y, it gave me this. So find the partial. Okay, we have another example. We are told to find the partial derivative of the function of z. This is the function of z, which is this. So let's look for it with respect to x now. Then don't forget, this is what a product, right? Product rule. So it means you have to apply a product rule, but don't forget you are looking for x first. So it means you have to take your you have to make sure it's clear, because if it's not clear, it's going to confuse you. Now looking for product rule, we say product rule is what we have v and we have what u. So for a product rule, we have v du dx plus u dv dx. So the differentiating with respect to x, then I will come here. What is my v? This is my u and this is my v, right? This is my u and this is my v. So then I will take this, make it here, differentiate this, I will have 1, then this one give me 0, so it means I will have this plus, then now keep this one constant, differentiate this with respect to x, so differentiate this will give me 2, this will give me 0. So reopening this, I will have this multiplied by 1, it will still give me 2x minus y. Y this one, 2 times x will give me 2x, then 2 times 3y will give me what? 6y. So I will have what? 4x plus 5y. Then differentiating this with respect to x, with respect to y now, which is for the partial derivative with respect to y, then it means I will have so the same thing, just like the way I differentiated it with respect to x, but now I will keep x constant. It's only what with respect what to y. So I will have, I take the, keep this constant, differentiate this with respect to y. So this will give me 0, this one will give me 3, which is this, right? Plus, keep this constant, differentiate this with respect to y. This will give me 0, this will give me minus 1. Alright, so open this bracket, I will have 2x times 0 is going, so I have 3. 2x times 3 will give me 6x minus y times 3 will give me this, right? Then 0 is going, minus 1 times s minus x minus 1 times 3 will give me what? Minus 3y. So I will have what? 5x minus what? 6y. So I will have this. So it means with respect to x I have this, with respect to y I have this. So I have another question here. If z equals what? 2x minus y all over what? X plus y, find partial derivative, partial differential of what? With respect to x and with respect to what? To y. And normally looking at this is what? A quotient. This is a quotient, right? It means you have to apply what? A quotient rule. So apply the quotient rule. We have partial derivative with respect to x. Don't forget, now for the quotient rule, I will have v du dx minus u dv dx all over what? V square. It's simple. I will repeat the formula: v du dx minus u dv dx all over what? V square. Now it means I should come where, what is my v? The first thing is for you to know what is your v and what is your u. This is my u and this is my v, right? This is my u and this is my v. So I will come v, I said the formula is what? V du dx. So my v, then what is du dx? This is my u bar, so I will differentiate u with respect to x. Now it will give me 2 here, this one will give me 0, so we have this minus, then u, what is my u? Look at my u here, u, then I will say dv dx, this is v, dv dx, I will differentiate this will give me 1 and this will give me 0 all over what? V square. This is what? V. So I have this. So the next is to open this bracket, it will give me this. You open this bracket, x, this one is 0, right? So it means 2x plus 2y, then here I have minus 2s, then minus y, right? So you sum everything to give me what? 3y all over what? This. Then with respect to y, I will apply the same thing, the same product rule, the same quotient rule, v du dx minus u dv dx all over v square, and don't forget you are differentiating with respect to y now. So it means what is v? Look at my v, look at my v, then du dx, look at my u here. So I'm differentiating this u with respect to y now. So it means here we have minus 1, this because this one will give me 0, so I have minus 1, then minus u, look at my u, which is this, then dv dx. So I'll differentiate this, it will give me 0. I'll differentiate this, it will give me 1. So you have this all over what? V square. So you open this bracket, you give minus 3x, then this will give me this. So with respect to x is this, with respect to y is this. So the next thing is for you to solve these equations. It's very simple. You differentiate with respect to y, then differentiate with respect to what? To x. You see what? The two different what? Answers. Now we are told, like the test that we are going to write very soon, this is the example, or you may see something like this in your test. We are told verify that u open bracket s comma t equals sine s cos kt satisfy the wave equation. Now this is very simple. We already know what is wave equation. Look at wave equation here, right? This is what the one-dimensional what wave equation. Once you solve and you see that this satisfy this wave equation, then it means your equation is correct, because this is what the standard wave equation. Now you come to the question. Look at the question. Sine s cos kt, right? So you try to look for this first. You try to look for this and you look for this. Then you try to equate them so that you can know whether you can get a factor, which is this. Now let's open it. We said our u function is this, right? And it depends on x and t, which are what? X and t. So the u partial differential of u with respect to x to this equation. Now you are differentiating x, right? So you are differentiating, it means everything here normal is supposed to give you 0. But this is what? Product function. So it means this one will be constant. You owe this one constant, which is this, and differentiate this with respect to s. Differentiating sine with respect to s, it will give you cos s. So we have this. So it means du ds is cos s. Then I have cos kt. Don't forget I'm looking for second order. So I will differentiate it again. So differentiating this again, so differentiate cos s with respect to s, it will give me minus sine s. So this one will still remain. So it means I've gotten second order. So I've gotten second order. Then the next is to look for what? Second order with respect to t. Then I'll come to this question again. It means I'll differentiate this. This one will be left constant because I'm differentiating with respect to t now. Don't forget this is product rule. So I will make this one constant. I will make it what? Sine x, right? Sine x will stay. So differentiate this with respect to t. With respect to t, it will give me minus sine, then k, minus k sine s sine kt. This is what I will have, du dt, to give me this. Then the second order, it means I should differentiate this again. So differentiating this again, another k will come outside, so it will now give me what? K square. So it means the second order of this is minus k square sine s cos kt. For the second order, so look at it, this is this, right? Why this? No, sorry. This is this. Why this is this? Then the next is for me to equate them. For me to what? To equate them. Substitute into what? The wave equation. You plug them in. For my wave equation, I have this and this. So when I plug them in, I will have this equals this, right? I will have this equals this. So from there, you can notice that there is factor that is remaining. Notice that the term sine s cos t, which is our original function u, appears on both sides. If we divide both sides by what? Our minus sine s cos t, assuming u is not equal to 0, then it means we have what? Our k square equals c square. So because of that, we say it satisfies what? The wave equation. Our c square is k square, which means c is k. Then it means z satisfies what? Our wave equation. Imagine you see this in your test now. Will it be difficult? It's just for you to solve it, and you have already seen that your k is c, and it means it's what? Satisfy what? The wave equation. Then also verify u s comma t, we have what? E to the power of what? Minus kt sine s. Satisfy, check if you satisfy what? The heat what? Equation. So the standard form of one dimensional heat equation is this. See, it's different from the first one. Now, for the heat equation, with respect to T is first order, but with respect to S is second order. So let's look for with respect to T first, which is what our first order. So we come to our equation with respect to T. This is the one that's having T. So differentiating this with respect to T, this one will remain constant. So I'll differentiate this. It means that we have minus K e to the power of minus kt. So I've gotten this. So the next thing is for me to get this. So du dx equals this now. So differentiate this with respect to what? To x. So this way I will keep this, which is this. So I will differentiate sine x, right? I will differentiate sine s, it will give me cos s. So the first order is this, right? Then for the second order, I will differentiate this again. If I differentiate it, it will give me minus sine s, which will give me this, right? So it means the second order will be this. This is the second order, right? This is second order with respect to s, which is this, and this is the first order with respect to t, which is this. So I will equate them. What you do now, the next thing is just to substitute the values you have. Remove this, put the value you have for this, which is this, right? Then remove this, put the value you have for this. You equate them, you see that k equals what? C squared. So because of that, you see is what? It satisfy what? The wave equation. Because you are saying that it's the same thing, it satisfies the wave equation. Now we are to show that the equation this e to the power of ex cos y satisfy what? The equation this, and don't forget this what? Second order Laplace what? One dimensional what? Laplace equation. Now the solution. So it's simple. You look for it with respect to x and second order with respect to y in second order also. So I have what? E to the power of e to the power of x cos y. So this is our equation, right? So for the first order, I will differentiate this. Don't forget cos y will remain. Cos y, differentiate es 1. So I still have ex, I will still have this. I will still differentiate it in the second order. It still give me this. It's still this, right? Nothing changes. But with respect to y now, I will differentiate with respect to y. This one will remain. I will differentiate this. It will give me minus sine, right? Minus sine. Yes, it will give me minus sine y, right? I will differentiate it again. It will now give me minus cos y. So it will now give me this. Now looking at this and this. So according to our Laplace equation, if you add this and this, it's supposed to give you 0. So add this and this. This plus this now. This, which is this, I have this, plus this, add them, it will give you 0. So because it gives you 0, then it means it satisfies what? The Laplace equation. So this is true. It implies that it satisfies what? The Laplace what? Equation. It's simple. So also we have some other functions that you are supposed to go through. You have a function u of e depends on x and y is called what? Harmonic, if it satisfies what? The Laplace what? Equation. That is, we have what? The second order of derivative of x plus the second order derivative of y. When you sum them, equals 0. Which now you should check which of the following functions are what? Harmonic, right? And don't forget what is harmonic now. I say u, when you have what? Second, this derivative you differentiate it with respect to s comma with respect to y, it's called harmonic if it satisfies the Laplace equation. And we have already given you what is Laplace equation. We said for Laplace equation, the second order derivative, if you add them, it will give you 0 before it can be what? Once you second order with respect to x and with respect to y in second order, if you sum them, it gives you 0. That is when it satisfies what? Laplace. So if this satisfy that Laplace, then it means it's what harmonic equation. So you check here to know which one is what which of them are what harmonic. So what it's telling you is that you check for what the second order derivative with respect to x, with respect to y, second order, sum them. If it give you zero, then it means that equation is what an harmonic what equation. So a fundamental mathematical theorem regarding mixed partial derivatives. So we said if you differentiate with respect to what y, then with respect to x, and also or you differentiate with respect to partial derivative of respect to x first, so then with respect to y, the two are supposed to be the same. So the theorem is what Clarion what theorem. So when now what I'm trying to say is that you are looking for partial derivative, let's say in second order, right? But this one is telling you x, y, not x comma y. So it means you differentiate with respect to x, then differentiate with respect to y, right? Or you differentiate with respect to y, then differentiate with respect to x. It's supposed to give you the same thing. If it gives you normally supposed to give you. So for it giving you, the theorem is called what? Clarion theorem. So find all first and second order partial derivative for each of the following what equation. So you check this and check if the what they satisfy what this theorem. So bye, have a nice day. This is what I just decided what to give what a summary of what the partial derivative. Here I don't want this class to be too long. That's why we did not put into consideration a lot of what equation. But if you have question, kindly comment on the comment section, then we will try to give a response to your question. And if you want the slide, then you can request for it. Bye, have a nice day, and don't forget Spark Scholar from idea to paper.